Rockets are incredible machines that have made it possible for us humans to expand our knowledge of the universe and our place in it, and to explore places never thought possible more and more over the years. However, rockets are very, if not the most complex machines ever invented, and rocket science is no easy thing to grasp. In this video, we're going to see just how rockets work with simple explanations, real examples, and even a real-life demonstration of me launching my own rocket to further illustrate these concepts. Let's get straight into it and truly understand what a marvel of engineering rockets really are, and how they push the boundaries of what's possible all the time. Rockets are all built and flown differently to achieve their specific mission objective. However, the most general goal of every spacecraft is to accelerate, to overcome the Earth's gravity and its massive atmosphere. Rockets aren't just designed to have some force of acceleration, but to provide continuous acceleration. In other words, when you are building up more and more speed exponentially over time without slowing down. To illustrate this a little better, imagine a cannon. It shoots a cannonball out of it. That cannonball is given a lot of initial force or acceleration very quickly from the cannon. However, that sudden force and acceleration very quickly diminishes. Rockets usually need to go far distances, meaning an initial boost won't do the trick. What a rocket essentially needs is the boost of being shot out of the cannon to occur continuously all the time, which seems impossible at first. However, not with engines. There are many different types of engines, such as ones that rely on air and ones that rely on internal oxygen, as I mentioned in my previous video. However, all provide the same goal of producing thrust. Rocket engines work by creating a reaction of both the fuel and oxidizer in the combustion chamber, which fires an immense amount of gas out the engine nozzle, propelling the rocket upward. The thrust generated by this action must be greater than the mass of the rocket in order for it to overcome gravity and leave the ground. This is measured in thrust-to-weight ratio, or TWR. The TWR of the rocket must be greater than 1 to leave the ground. As an example, the SpaceX Starship, fully stacked, has a thrust-to-weight ratio of 1.5. One thing you may notice when watching any rocket launch really, is that when the rocket engine initially ignites, the rocket is propelled upward quite slowly, but then goes faster and faster as it ascends. This is not because more thrust is being generated, but rather because as the rocket fuel burns away and there is less and less of it, the rocket's overall weight is reduced, meaning the mass of the rocket gradually gets more and more easy for its engine to overcome, increasing its speed. However, rockets don't always need to continue to accelerate. When a rocket is in space, it will speed up enough to eventually reach its destination, but will then cut its engines. Wouldn't the rocket's speed diminish? In space, there is no air of any kind, meaning that air resistance is not really a problem. Air resistance is in the atmosphere and is what slows things down. However, space is an empty void filled up by little planets, moons, stars, and galaxies. This means that if you accelerate to a certain speed, you will continue going that speed forever. Imagine a ball in a completely empty universe. If I threw that ball at 10 kilometers an hour in a direction, it would continue going in that direction at the exact same speed as I threw it forever. This applies for rockets and anything else really too. The only thing that, except thrust, can change an object's speed or trajectory is gravity. More specifically, the gravity of other objects in space. Now that we have covered some of the basic concepts of rocketry, let's see how rockets put all of these concepts into action. A rocket is usually made up of 4 separate systems inside it, and they must all work together to complete the mission objective. The first is the structural system, which is the frame around the rocket that we see on the outside. The structure of the rocket itself is made of relatively lightweight materials, as the main weight of the rocket comes from the fuel and payload, and you want your rocket to be ideally as light as possible. Moving inside the rocket, we have the payload system, which could hold, for example, a satellite, crew capsule, spacecraft, or part of a space station. The payload or cargo of a spacecraft is, depending on its size, mass, and shape, sometimes surrounded in fairings to protect it as the rocket ascends through the atmosphere. These fairings will break off, revealing the payload inside once at its destination. The next is the guidance system, composed of radars and computers to make the rocket function and make sure it stays on track. The last and most important part of any rocket is the propulsion system. This system is what generates the thrust for the rocket to leave the Earth, consisting of the fuel, combustion chamber, and the engine itself. If, say, our rocket is running on liquid fuel, then there will be a tank for the fuel and a tank for the oxygen. When the countdown reaches 0, The fuel and oxygen travel down to the combustion chamber, where they are mixed and burned together, and the explosion from this sudden impact shoots out down the engine nozzle continuously until the fuel is run out, generating the thrust needed to get to the stars. While rockets vary significantly in size, shape, mass, and thrust, and their payload and mission objectives, these concepts go the same for all of them. To further illustrate these concepts, and also to have a little fun, I bought and assembled a model rocket to launch. Let's cut to real life to see how this went. As you can see, that rocket launch was truly magnificent, so let's break down everything that happened in that 20-second launch. First, the fuel ejected violently out of the engine, and the rocket cleared the tower. The very light weight of the rocket itself combined with the thrust generated meant that this rocket had a very high TWR, and ascended into the sky very quickly. However, this massive thrust meant that the fuel ran out quite quickly. The rocket then opened the nose cone and the parachute expanded, slowing the rocket down as it descended back to the Earth. From this video, it is quite clear that rocketry is complicated, and the concepts covered in this video is nothing compared to the immense and complex challenges scientists, engineers, and the astronauts themselves have to tackle to make spaceflight possible. However, all of this hard work pays off as rocket technology continues to grow and advance exponentially, and get us humans closer to truly living beside and reaching the stars, one ejection of hot gases out of an engine nozzle at a time.